Hello class, in today's lesson we are going to learn how to name alkenes, alkynes, alcohols, halides, and some simple amines and ethers. So first, an alkene is the same as an alkane, but it has at least one double bond. These are referred to as unsaturated hydrocarbons. Unsaturated means that each carbon does not have the maximum number of H's it could possibly have. Typically, a single carbon by itself can have up to 4 bonds, and the number of hydrogens it has is based off of how many other carbons it's bonded to. If it doesn't have the maximum number of carbons, then a double bond is necessary, or even a triple bond, to satisfy the octet for those carbons. For nomenclature rules, it's fairly similar. The ane suffix from alkane changes to an ene for alkene. So before we add a 4-carbon chain, that would be butane. If there's a 4-carbon chain with a double bond in it, it would become butene. Same thing with hexane. If it is a 6-carbon chain, but it has a double bond, it goes from hexane to hexene. In terms of naming, the same rules as an alkane apply when it comes to identifying functional groups and substituents. You have to count the largest parent chain so that the double bond gets the lowest number. We have to identify where in the chain the double bond occurs, especially when you have multiple carbons, and that double bond can be just about anywhere. We assign the lowest possible number to it. So on the 2nd carbon here and the 3rd carbon, you see the double bond stretches from the 2 to the 3 position. We give it the number 2 because that's the lowest possible number in the chain where the double bond starts. When there are substituents, we still number so that the double bond gets the lowest number. We say that the double bond gets priority. So even though the first substituent occurs over here, if we were to number 1, 2, 3, 4, 5, that would be an incorrect numbering scheme because the double bond starts on 3, when if you number in the other direction, 1, 2, 3, 4, 5, the double bond would start on 2. So you do want the double bond to have the lowest number possible, even if it means the substituent, the branch sticking off of your chain, has a higher number. If there's more than one double bond, we need to use prefixes to represent that. So if there's more than one double bond, we use di. If there's more than 2 double bonds, we use tri. And then you just put that in front of the ene portion. So the parent chain, this is really important, the parent chain will always be the one with the most double bonds, even if the parent chain is not the longest. So go ahead and try these examples so far before we progress. You should pause and try these 3 structures now. Okay, welcome back. So the first one, we have a 5-carbon chain. So that is going to go from pentane to pentene. We need a number to represent the double bond, so 2-pentene, and then a number to represent our substituent. It's a methyl group, so this would be 4-methyl-2-pentene. So let me clean that up a little bit. 4-methyl-2-pentene. Now there is another way you can do this, another system that is also correct. 4-methyl, the prefix for the number of carbons, pent, and then you put the number in between, 2-ene. You see that is common fairly often as well. Both of them mean the same thing. I tend to prefer this method when we're dealing with simple alkenes because it's just easier to read and pronounce, flows off the tongue a little better. But when you've got multiple types of high priority substituents, as we'll see when we get to some alcohol problems that also have alkenes in them, this system where you put the number directly next to the feature it's describing will be useful for us. In this second example, we have a number system. We have to number from left to right. So we have 1, 3, and this is a 5-carbon chain. So penta, and then we need the prefix diene. So 1, 3, penta, di, because there's 2 double bonds, and then ene. For this next one, we've got 7 carbons. So it starts on 1, 3, and 5. Since there's 3 double bonds, and it's a 7-carbon chain, we need hept. And then, so hepta, the prefix tri, and then we end with ene. 1, 3, 5, hepta, triene. As I stated before, the double bond takes priority for the parent chain. So in this particular example, we see that the longest chain is, let's see, 1, 2, 3, 4, 5, 6, 7 carbons long. But the problem with that is that it only contains one of the double bonds in the parent chain. This chain, 1, 2, 3, 4, 5, 6 carbons long, is actually the better parent chain because it includes both double bonds, and the double bonds have the lowest possible number. So what you need to do is number in such a way: 1, 2, 3, 4, 5. Did I miss a carbon? I did, I'm sorry. 1, 2, 3, 4, 5, 6. 1, 4 is one of the possibilities for naming this chain. The other way you could do is 1, 2, 3, 4, 5, 6, and then 2, 5 is the other possibility. We want a number in the direction that gives us 1, 4, because those are the lowest possible numbers. So then, if we were to tackle the rest of this one, on my 4th position, I've got a 4-carbon group that is a normal butyl group, so it's just butyl. And then I've got a methyl group on 5. Remember, you have to alphabetize, so we have 4 butyl, 5 methyl, and then we need numbers for our bonds. 1, 4, hexa, and then the prefix diene would be the correct name for this example. So as I said, the 1, 4 would win out over the 2, 5. So we go with that parent chain instead. And I guess I forgot that I had an opportunity for you to name this one, but you'll get the hang of it as we do some more problems. For cycloalkenes, this is a ring that has a double bond in the ring. The double bond still gets the lowest number in the ring, even if there are branches or substituents. So the alkene still takes priority. The double bond has the priority when it comes to lowest numbers, even if you have branches. If only one double bond is in the ring, you don't need any numbers because we assume the double bond is on 1 anyway. So in this first example, I have a cyclohexane, but there's a double bond, so it just becomes cyclohexene. Now take a look at the other one. Now this one's kind of tricky because we have 2 double bonds, and we want to number in such a way so that the double bonds have the lowest numbers possible. Okay. I also see a substituent here, so I'm going to make that carbon number 1. 2, 3, 4, 5, 6 is one option. I could also go in a different color. If this is carbon number 1 still, I could number the other way: 2, 3, 4, 5, 6. I'm going to number clockwise on this one because my double bond ends up on 1 and 3, which is better than 1 and 4. So this would be 1-methyl and then 1,3-cyclohexadiene. And I just realized I must have had an error on my key when I originally did this. It should be 1,3, because 1,3 would give you the lowest possible numbers. I must have made a mistake. So yes, it's cyclohexa because it's 6 carbons. We need the di prefix because there's 2 double bonds. And then it's 1,3-cyclohexadiene. And that gives the lowest possible numbers for the double bond. So as you've seen so far, the general formula whenever we're naming something is a number that identifies the location of your substituent, followed by the parent chain, and then the functional group suffix. So yes, alkane, alkene, alkyne is a functional group. Those represent different types of hydrocarbons. But as you'll see when we get into other naming systems, you also have a different functional group suffix for alcohols, for amines, for ethers, for carboxylic acids. They're all named in a slightly different way. So here's some practice. Go ahead and draw these. Pause the video now. Okay, you can check your work. So we have 3,3-dimethyl cyclopentene. I would start with the cyclopentene. We know that cyclo means it's a ring, pent means we have 5 carbons, and ene tells us there's a double bond. When you place your double bond, remember that that double bond gets a 1. So we go 1, 2 in terms of our numbering system. And then on this third carbon here is where the methyl groups end up. So we have 3,3-dimethylpentene. Same thing, start with your parent chain, 2-hexene, draw a 6-carbon chain, put the double bond from 2 to 3, and then on the second position is a methyl group. On the third position is another methyl group. Whoa, what happened with my pen there? And then on the sixth position is a bromo group. Briefly talked about halides. Those are your chlorine, bromine, iodine, and fluorine. Those are your halides. And so you see fluorine, it becomes fluoro, bromine is bromo, etc. I'll talk about that a little bit more after we talk about some alkynes. Alkynes are also another hydrocarbon class, this time with a triple bond. Because of the triple bond and the hybridization of those carbon atoms, we end up with a linear molecule. So it's really important here to recognize that in this particular example, there are 5 carbons. Here's the first, and then there's 1 on either end of the double bond. This makes 4, and then 5. Whenever I said double bond, I meant triple bond. Whenever you have a triple bond, it has to be linear, and the 2 carbons sticking immediately off of the triple bond also have to be straight. So there should be a straight line here and a straight line here sticking off of your triple bond. So you should always have 4 carbons in a row wherever there is a triple bond. And then you can resume making your angular or bond line structure format. We have the same rules as an alkane and an alkene when it comes to naming, but we use -ine, Y-N-E, as the ending. What if there's a double bond and a triple bond? Well, I mentioned earlier priority. There's actually a priority of naming systems for each functional group. So alcohols have the highest priority. They always take the priority in the parent chain if they are present. If the alkene is present, if there's a double bond, an alkene takes priority over an alkyne, meaning your parent chain needs to end in -ene. If you have an alkyne, then that would be the highest priority. And you'll see actually that halides have the lowest priority. So usually halides are substituents. You don't typically see them in the parent chain. For alcohol nomenclature, this is the one, like I said, that has the highest priority. We change the ending to OL, so ol. Not to be confused with aldehyde nomenclature, which is AL or AL. So you'll see ALs and OLs at some point in time. Primarily, I just want to focus on alcohol nomenclature because we see those a lot. You identify the location of the alcohol group, just like you would as a branch or a substituent. And then you name the parent chain as normal. So in this example, we have propane, which is a 3-carbon chain. On the second carbon is our alcohol group, our OH group. And so we name it propanol. Now, the common way to name it is naming the branch, naming the carbon chain is actually a substituent of the alcohol. So this is actually the isopropyl group. So they commonly refer to it as isopropyl alcohol, which is actually something many of you have probably encountered before. They usually use it as a disinfectant. For the purposes of what we're doing, I would continue to name using the IUPAC system. If there are alkenes or alkynes within an alcohol group, both have to be numbered. The highest priority still goes to the alcohol, so the alcohol should actually have the lowest possible numbers, not the double bond. The double bond number goes in the same place as before. The OH numbers go in between the parent chain and the OL suffix. So as I mentioned before, when we were first looking at alcohols, or not alcohols, alkenes, one of the ways they might have named this was cyclohexene, and they show that number preceding the functional group it's describing. So this is showing that the alkene is on the 4th position. So you see they do the same thing here with the alcohol. The alcohol groups OH are on 1 and 3. So they put those numbers before the OL prefix. And since there are 2 alcohols, they have to use the prefix di. So we get a diol. So all in all, this is numbered clockwise 1, 2, 3, 4, 5. This would be 6, with the OH groups having the lowest possible numbers. And then we end up with 4-cyclohexene 1,3-diol. For alkyl halide nomenclature, so alkyl halide or alkyl halide, same thing. It's the name of the halide and the parent chain with the number. Like I said before, bromo, chloro, fluoro, and iodo are the way you write the branch names. In this particular example, I've got propane, 3 carbons, and the bromine is sticking off of the first carbon, so I have 1 bromo propane. When you are naming it with the common name, you name the carbon chain as if it's a substituent of the halide. So propyl bromide would be the common name, but again, we're sticking with IUPAC names for the most part, so you would see bromo propane. The last group we have to look at are ethers and amines. What I will say with these is this is how you name them when they are simple, common ethers and amines. I wouldn't really use this method or classify this method as IUPAC officially. This is only if you've got 1 ether oxygen or 1 nitrogen in your compound, and you name the carbon chains as if they are branches sticking off of the O or the N. You name them in alphabetical order, and then you tag the word ether or the word amine at the end. So this group here is your secondary butyl group. This group here is a tertiary butyl group. S comes before T, so it's sec butyl, tert butyl, ether. There's technically a different way to use this in IUPAC form, where you name the longest parent chain, and then the shorter chain, they name using the prefix. So if you had like a 2-carbon chain, that is F, and then they change the suffix to oxy. So they would say whatever the parent chain is, and then the number, and then ethoxy. We're not going to use that system for this part of the course because we just won't deal a lot with ethers and amines when we're doing our reactions at the end of the semester, but it is good to know how to name some of the simple ones. Here I've got a secondary butyl group as well, and it's sticking off of the amine, so this is sec-butylamine. Here I've got 3 methyl groups, so it's trimethylamine. Notice that when I have 1 branch sticking off of my nitrogen, I have 2 H's. If I had 2 branches sticking off of my nitrogen, I would have 1 H, and then when there's 3 branches sticking off of my nitrogen, I have no H's. Technically, there are lone pairs here sticking off of the nitrogen, just like there are lone pairs sticking off of my oxygen. Some common or trivial names for alkenes that you may come across. Ethene is commonly referred to as ethylene or ethylene. The reason they do that is they just view the carbon chain as a substituent of the double bond. So that's a trivial name that you'll see. Same with propene, they'll call it propylene, or butene will be butylene. There are some other common names you'll see. When there's a carbon that is participating in a double bond, it's referred to as a vinylic carbon. The carbon adjacent or right next to a carbon participating in a double bond is called an allylic carbon. Those terms will be very important when it comes to reaction mechanisms and classifying organic reactions, because we need to know the difference between an allylic carbon and a vinylic carbon, but keep those in the back of your mind for now. For some of the haloalkenes or the alkyl halides, very similar process. You still name the double bond with the lowest possible number, and then the halogen turns from ene to O, so chlorine becomes chloro. But you'll notice that there are some trivial names. This chlorine group is in the position adjacent to a double bond, so they call this vinyl chloride. And then, or not adjacent, it's directly attached to the carbon of a double bond, so it's called vinyl chloride. Here, there's a carbon that is adjacent to a double bond, and the chlorine is attached to that carbon, so it's called an allyl chloride. Some examples you might see, it's good to know the trivial names for later on when we get into reactions. That is all for today's lesson.